Hello everyone, this is Team 10. Our project is a smart scooter incorporating YOLO framework, and the team is Jay Jagtap, Noah Lozevsky, and Tyler Sattler. So the motivation behind our project is to create a security feature in bikes such as Lime, which are the electric scooters. So right now these bikes ride at a very high speed and does not have a feature which could tell the user whether a vehicle or a pedestrian is coming on the road. The solution we propose is that we want to integrate a YOLOV3 or a tiny YOLOV3 network into an iOS app, which could be mounted on the electric scooter and which can alarm the users in real-time basis if there is some security issue, like a vehicle comes in, a truck comes in, or there is another person who is walking by and the user doesn't know it. So our proposed solution integrates the YOLOV3 model, which can function as an alarm-based system. So we are using Google's Open Image V6 dataset. So the images are clipped into 416 into 416, and the classes we have selected there are 26 classes, which we generally find in road, like person, trees, wheels, or other vehicles. And each class has around 2,500 images, and we have split it into 90% train and 10% testing images. So this Google's Open Image V6 dataset gives us the images in bounding boxes so that we have the coordinates in the image where exactly our object is located. So this is a pipeline. So we have written our code in PyTorch. We first import our images from a dataset into the PyTorch model, then convert it into the YOLOv3 format, train it on a PyTorch model, and convert it into an ONNX model. So ONNX is basically Open Neural Network Exchange, which is a standard format for representing machine learning models, which could be used for transfer learning and borrowing weights from other models. To convert it into an iOS app, we need to convert it into a Core ML. So Core ML is an Apple framework that allows developers to easily integrate machine learning models and make them into apps like iOS or for Mac OS or iOS. So we import the weights and create an iOS app which gives real-time object detection.
Cool. So in order to train a high-performance object classifier or object detector such as the YOLO framework, a lot of different image augmentations during training must be applied. We basically had 8 parameters in terms of the image augmentation going into the network. We have an example here in OpenCV showing some of the HSV variations, including the saturation, hue, and intensity value before and after processing. We also have directional augmentations, rotational, translational, scaling, and shearing, as well as the input image size being varied with padding. We also implemented a mosaic model in terms of developing the actual input image. As you can see, the input for our framework was 416 by 416, but some of the images could be scaled, resized, and randomly tiled across to make one full image and padded with zeros on the boundaries that don't incorporate that. So this is a little bit about like the actual framework at play that we trained. So the highlights of this is that there's actually 3 different YOLO layers, and YOLO is named that way for the acronym You Only Look Once. So each one of those 3 different YOLO layers is actually evaluating different portions of the actual input image at different scalings. So it's actually, before it actually gets a final output, it's incorporating data from the small scale, the individual bounding boxes, and then the next size up, and then the full image. So this is a little unique in that sense. As you can see to the right, the output vectors that we're actually getting are composed of several values. We get the bounding box starting X, Y coordinates, as well as the width and height. These are normalized values on the scale of 0 to 1 with respect to the actual input image dimensions, which allows us to resize any aspect ratio, and as long as we keep the aspect ratio constant, it should, and pad the rest, it should output correct bounding boxes. We also have an objectness score, which is the probability or confidence value that the actual vector output for that specific box has one of the classes that we trained it on. And then to the right, we have the class scores, which are the actual probability or confidence values for that class. So when we get an output, we have a confidence threshold for the objectness, and then we use a softmax on the actual class scores. In terms of hyperparameter tuning, YOLOV3 is a little finicky, as well as most other object detecting models. We use 3 different optimizers: Atom, Standard, Stochastic Gradient Descent, as well as a custom LR scheduler designed by Joseph Redmond, who is the inventor of YOLO. He has a lot of different parameters that we played around with a little bit, but most of it needed to just be set to what he found was the best. Some of the other things we changed were varying the batch size, number of epochs, as well as the image augmentation parameter probabilities.
So on the left are results. You can see our loss and mean average precision across epochs converge to local minima. Compared to our baseline, which is tiny YOLO, we achieve a map score of 0.17 compared to their reported 0.16. The right demonstrates images from our test set with the associated bounding boxes. The bounding boxes shows that these objects have an objectness score greater than 70%, meaning the algorithm has a confidence of 70% or greater that the object is within our class. The value on the box is the class confidence score related to the class it predicted. This is not a probability, as the confidence score does not add up to 1 for all classes. Our current iPhone implementation allows for 50 or more objects to be detected per second with our app, running at 25 frames per second. Shown on the image to the right, the 2 slide bars change the frames per second of the app, while the other slide bar changing the objectness score threshold. Lowering the threshold as shown allows for more similar objects to be detected and interpreted as one of our input classes. For instance, this is not a stop sign, but since we lowered the confidence score, it's detecting it as a stop sign because it looks similar. Here we have 2 live demos. I'll show the first one. On the left, you can see the app in action. Just walking around, it's detecting a bench to the right, it's detecting cars further down. Once it looks at the feet, it detects a human. As you see, it's detecting more cars as they're driving around. And some people walking down further down the sidewalk. On the right shows changing the hyperparameters within the app itself. So as we go up to this sign, once again, we're going to lower the confidence score, and it's going to start detecting a lot more objects around and giving it a label that's within our classes. In this case, it's detecting the do not enter sign as a stop sign. So in conclusion, we create a phone application incorporating object detection to improve electric scooter rider safety. We use the YOLOV3 framework and demonstrate a 0.17 mean average precision compared to the tiny YOLO's 0.16 map score. For future work, we'll incorporate real-time feedback and notifications for riders. As an example, it will say watch car when a car suddenly comes into a frame, or slow down when entering a high traffic area.